Before you begin your 12.7 notes, I have a riddle for you I want you to think about. A bear leaves his home and walks 5 miles south. He makes a right turn, a 90-degree turn, and walks another 5 miles. The bear turns right again, another 90-degree turn, and after walking 5 miles, he returns to his home. So the question is, what color is the bear? So think about that, and maybe you'll have an answer to that riddle before you finish these notes. Hello, geometry students. As you know, all this year we have been studying what's called Euclidean geometry based on the work of Euclid, who lived thousands of years ago. And so just for today, we are actually going to step away from Euclidean geometry. In fact, here's a picture of Euclid reading a Dear John letter. If you don't know what a Dear John letter is, that's a breakup letter. So our letter says the following: Dear Euclid, we've learned a lot from you, but it's time for us to move in another direction. Love, your students. P.S. Can we still be friends? I hope so, because we're going to get back to Euclidean geometry after today. But for today, we're going to step away from Euclidean geometry and look at a different type of geometry called spherical geometry. And that's the geometry of a sphere. So what we'll do mostly today is just compare Euclidean geometry to spherical geometry. So let's start with the ideas of those undefined terms that we began our study of Euclidean geometry with. The first undefined term we talked about was a point, and as you recall, a point is simply just a location in space. It did not have any dimensions, no length, no width, and we named a point with a capital letter. Well, similarly, that's a hard word to say, in spherical geometry, a point is a location on a sphere. So if you want to place a point on this sphere, and let's give it a name, we will call points or name them with capital letters in spherical geometry, just like we did in Euclidean geometry. Okay, let's talk about the next undefined term, the idea of a line. Remember, in Euclidean geometry, a line is simply a one-dimensional straight path that is endless in both directions. Well, in spherical geometry, the idea of a line is something different. A line is actually what we call a great circle. Okay, we mentioned great circles the other day, and you'll recall, if you think of the equator of the Earth, that would be an example of a great circle. A great circle would be a circle that has the same radius as the radius of as the sphere. So the sphere and a great circle would share a radius. So an equator, or the equator, would be an example of that. And if you look at all these longitudes, those are also examples of great circles, because they would all be circles whose radii are the same as the radius of the sphere. So a line is a great circle, and it must pass through two poles. And what would poles be? Well, we're used to talking about on the globe, on the Earth, the North Pole and the South Pole. But a pole can be any two endpoints, which would be the endpoints of a diameter. So if you could imagine a point here and a point here, there could be a pole that is perpendicular to the North and South Pole. It would be just a diameter, and the endpoints of that diameter would lie on the equator. So a line in spherical geometry must be a great circle, and it must pass through poles and share, as we already mentioned, share a radius with the sphere. Okay, now I want to stop for a minute and just talk to you about one example of where lines matter in spherical geometry. So several years ago, my husband and I actually had the opportunity to fly from Chicago to Tokyo. So when I knew I was going to be flying from Chicago to Tokyo, I looked at a globe and I found Chicago. Now it's kind of hard to see because the word New York has been written over the word Chicago, but here's Chicago and here's Tokyo. So I looked at a globe and I thought, well, it looks like we'll fly across the United States and then we'll fly across the ocean, the Pacific Ocean, and we'll end up here in Tokyo. So I was very surprised when I got on the plane, and here on this map, if you looked at a flat map, that's what it would look like, straight across the United States, across the Pacific Ocean, and then ending up here in Tokyo. So I was very surprised when I got on the plane and I was looking at the literature in the seat back pocket, and it showed the flight path where from Chicago, rather than going straight across the United States and across the ocean, we were actually going to go up through Canada, through Alaska, stay close to these land masses, and end up here in Tokyo. So my thinking was, well, I guess the pilot wants to stay over land for a longer amount of time and not be flying over water. But what I didn't realize is that if we had taken this path, it would have taken a lot longer to get from Chicago to Tokyo, and it already was a very long flight. So what we're going to do right now is imagine if you were a bird and you could fly up here and you could be looking down at this arc right here. And what this is actually the arc of a great circle. So if you could imagine a great circle through this whole around that would encircle the entire globe, it would be a circle whose radius would be the same as the radius of the sphere. But imagine if we could fly up above and we could look down at a bird's eye view of that path. So let's look at this next slide. This would be the bird's eye view. So imagine we've just flown over kind of on top of the earth and we're looking down at that flight path. So you can see how it clearly is the shortest path from Chicago to Tokyo, because what this actually is, it's an arc of a great circle. So again, imagine a great circle that encircles the earth, and this path is just part of that great circle. And you can see that this path is quite a bit shorter than what this path would have been. So again, the path that you would take if the earth were flat, you know, the straightest distance in Euclidean geometry, the shortest distance is a straight line between 2 points. But you can see on the earth, that sphere is that arc of a great circle is far less flying time. Imagine if you were the airline company, you want to get your passengers there in the least amount of time, you want to use the least amount of fuel, so you're going to take the shortest path, which isn't this path, it is actually this arc of a great circle. Let me show another example. Imagine if we wanted to fly from Bombay, India to New York City. Okay, again, on a flat map, it looks like the shortest distance goes across the top of Africa, across the ocean to New York. That appears to be the shortest path on a flat map. But again, imagine what we're going to do is take the actual flight path that an airplane would take, and imagine if you could fly above and look down at a bird's eye view of that arc, and the arc would look like this. All right, it is, as you can see, from Bombay to New York, taking this arc. Imagine a great circle again that encircles the entire globe. Okay, the arc of this great circle is a far shorter path than taking the path that you would take on a flat map. So just to say one more time, that a line in spherical geometry is a great circle. So like the equator or any of these longitudes. Okay, or it doesn't have to be any of these great circles that are perpendicular to each other. You could have a pole here and a pole here, and then a great circle that surrounds the entire Earth. All right, so we've talked about points and lines and compared Euclidean geometry to spherical geometry. Now let's talk about planes. All right, so in Euclidean geometry, a plane, remember, is a two-dimensional flat surface that's endless in all directions. Now, we talked last August about the fact that when we sketch a plane, we sketch this parallelogram, but that's a limited idea of what a plane is. Remember, a plane is infinite. It's infinitely wide and it's infinitely long. So it does extend forever in all directions. It's just impossible to draw that, so we draw planes as parallelograms. In spherical geometry, on the other hand, a plane is the surface of a sphere, okay? So it is not infinite like a plane in Euclidean geometry. A plane in spherical geometry is just the surface of the sphere, so it is finite. All right, so now let's start talking about the postulates that we first learned when we learned Euclidean geometry. The first postulate we learned was that through any 2 points there exists exactly one line. So let's sketch a couple of points. Let's give them names. Let's call them points P and Q. Okay, so if we have 2 points, Euclidean geometry tells us there's exactly one line that passes through those points. In spherical geometry, on the other hand, through any 2 nonpolar points, So those would be 2 points like Chicago and Tokyo that we looked at earlier. Those points do not exist on poles. If you have two nonpolar points, there's exactly one line. But if we have any polar points, spherical geometry tells us that through any two polar points there are infinitely many lines. Infinitely many lines. A good example of that would be, again, to look at a globe, look at the North Pole and the South Pole. You can see that there are many, many longitudes that pass through those two poles. And what we have drawn here is just a subset of all possible great circles that go through those poles. So there are actually infinitely many lines that go through any two polar points. And again, it doesn't have to be the North Pole and the South Pole. A pole I remember polar points would be any points that are endpoints of a diameter of the sphere. So pick any polar points, and there would be infinitely many lines that pass through those two polar points. So let's continue comparing Euclidean and spherical geometry. So you might want to put a heading on this column. Remember, these are facts and information about Euclidean geometry, and then this column was what we're learning about spherical geometry. So the next postulate we're going to look at from Euclidean geometry is this one. You'll remember that given a line and a point not on a line, there exists exactly one line through the point parallel to that given line. Now that postulate was called the parallel postulate. So let's just draw a picture of it. So let's draw a line. Let's call it point or line L, and then a point not on the line. The parallel postulate says there exists one and only one point that passes through, one and only one line that passes through that point that would be parallel to the given line. Okay, so comparing that to spherical geometry, let's take a look at what this says. Given a line and a point not on a line, okay, like for example, you could draw a point right here. So remember, when we say the word line in spherical geometry, we mean a great circle. So given a great circle and then a point, why don't we go ahead and call that point P, that's not on the circle. Okay, point P that's not on the circle. In spherical geometry, there actually exists no line through the point parallel to the given line. Now remember, you might look at these circles and say, well, these circles appear to be parallel, they don't intersect. But remember, this circle that you're looking at, if it were on a globe, we'd call that a latitude. That is not considered a line in spherical geometry because it's not a great circle. All right, so we can just summarize that and say there are no parallel lines in spherical geometry because if you have a great circle and a point not on that great circle, there isn't going to be another great circle that passes through that point parallel to the given line. All right, the next postulate says the following. Well, actually, this is actually the ruler postulate that says the distance between 2 points. Let's draw a couple of points and call them P and Q. Let's draw a segment through those 2 points. The ruler postulate guaranteed that the measure of that segment is positive and unique. In other words, there's one and only one measure from point P to point Q. However, in spherical geometry, let's take, for example, the 2 points A, the 2 points A and B. All right, well, if I want to travel from A to B, I could travel along this minor arc. So let's go ahead, let's highlight that. Okay, so I could take the shortest path from A to B, but I also could take a different path from A to B. I could go through C along this major arc. So in other words, the distance from A to B is not unique. I can have a shorter distance from A to B, or I can have a longer distance from A to B along that great circle. All right, so the distance between 2 points then is not unique, and that distance will always be an arc of a great circle. Okay, so for example, my path that I flew from Chicago to Tokyo, that was an arc of a great circle. Now, and that distance was not unique. The pilot could have taken off and gone in the opposite direction and flown the long way around and taken a major arc. We would have gotten from Chicago to Tokyo, but it would have taken a lot longer. So the distance between 2 points in spherical geometry is not unique. All right. Another thing you'll remember from Euclidean geometry, this one was actually a theorem, and we proved this, and that is that the sum of the measures of the angles of a triangle is always going to be exactly 180 degrees. So let's draw a picture of that. Let's draw a triangle, and let's call its angles A, B, and C. Then we proved that the measure of angle A plus the measure of angle B plus the measure of angle C totals 180 degrees. That is always going to be true for a triangle. However, in spherical geometry, that is not necessarily the case. Do you remember the polar bear that we, oops, I just gave away the, I just gave away the riddle. But remember the riddle that we talked about? We said if a bear left his house, he walked south, made a right turn and walked for a while, made another right turn and walked, he would return home. So the question was, what is the color of the bear? Well, that bear would be a polar bear. He left from the North Pole. That's the only way he could return home after 2 right turns. So the answer to the question, what is the color of the bear? It's white. So in spherical geometry, the sum of the measures of a triangle can therefore be more than 180 degrees. If you look at the triangle that the polar bear's path took, there's a right angle here and there's a right angle here. Well, 90 plus 90 is already 180 degrees, so it doesn't matter what the measure of this angle is. We have exceeded that 180 degree limit. So in spherical geometry, the sum of the measures of the triangles can be more than 180 degrees. All right, so that's just an introduction to spherical geometry, and we're not going to get too deep into it, but I do just want to do one more example real quick. Let's say, if you recall the story of Romeo and Juliet, let's say that somewhere along their story this happened. Romeo and Juliet decide to take a break from each other after having an argument. Romeo leaves Verona, Italy, and starts walking east. Juliet starts walking west. How would this story end in Euclidean geometry, and how would it end in spherical geometry? And then we're going to mark the diagram to support our conclusion. So let's say in Euclidean geometry, if the world were flat and Romeo started walking to the east, okay, his path would look like that in a flat world. Okay, Juliet starts walking to the west. Now, in Euclidean geometry, these 2 rays that we have drawn, okay, they're opposite rays, and together they form a line. Well, what do we know about lines in Euclidean geometry? They extend forever in both directions. So if this were the case, Romeo and Juliet would never meet again because they would go forever in opposite directions. Are Romeo and Juliet walking on the line? Well, the answer to that is yes, because we are looking at a pair of opposite rays. Okay, now let's look at the same scenario, but this time in spherical geometry. So Romeo starts walking to the east. Juliet starts walking to the west. Now, let's answer the question, are Romeo and Juliet walking on a line? Well, this appears to be the center of the Earth, but I think you know enough about geography to know that the equator does not go through Italy. So obviously the Earth has been rotated toward us a little bit. So this is not the equator. So therefore, Romeo and Juliet are not walking on a great circle. So the answer to the question, are they walking on a line? The answer would be no. You might want to make a note because they are not walking on a great circle. The only lines in spherical geometry are great circles. All right? But how about the end of the story? If Romeo starts walking to the east and Juliet starts walking to the west, since they're walking on a sphere, eventually they would meet up again. So in spherical geometry, the end of that story would be a little bit happier. All right, so what you're going to do right now is work on your classwork. So when you get that done, check with me so we can make sure your answers are correct. And once you're done with that classwork, you'll be done with spherical geometry.